Hi, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the properties of superconductors and then we'll see the Meissner effect. So, in this topic, we are going to cover the properties of superconductors and then effect of magnetic field, then the Meissner effect of current, then we shall see the references regarding to this topic. So let's see the properties of superconductors. So superconductivity is a low temperature phenomenon. The transition from normal state to superconducting state occurs below the critical temperature. The transition from normal state, that is normal conducting state, that is when we are taking conductors, so it can be changed as a superconductor below the critical temperature. So the transition from normal state to superconducting state occurs below the critical temperature. The different materials will have different critical temperatures. Different materials will have different critical temperatures. So, the current once set up in a superconductor persists for a long time due to the zero resistivity. So, the current once we set in superconductor, it would be continue for a long time because of its zero resistivity. Superconductors do not allow magnetic field through them and behave as a diamagnetic material. So superconductors do not allow the magnetic lines of forces. They do not allow the magnetic lines of forces through them so that they behave as a diamagnetic material. So this property is expulsion of magnetic field is known as Meissner effect. So this property, so the property which it is ejecting the magnetic lines of forces is known as Meissner effect. The magnetic field at which a semiconductor loses its semiconductivity and becomes a normal conductor is known as critical magnetic field, which denoted by Hc. Critical magnetic field Hc. So, the magnetic field at which a superconductor loses its superconductivity. So, at which magnetic field the superconductivity property destroyed and become as a normal conductor is known as critical magnetic field Hc. Superconductivity occurs in metallic elements in which the number of valence electrons lies in between 2 and 3. So the metallic elements valency electrons lies in between 2 and 8. Those can show the superconductivity property. Materials having high normal resistivities. Materials having normal high resistivities exhibit superconductivity. And superconductivity materials are not good conductors at temperature. Superconducting materials are not good conductors at temperatures. So this is the resistivity of mercury. This diagram shows that the resistivity versus temperature of mercury. So here when we are taking temperature along x-axis T, on y-axis resistivity rho. So when observing this graph, the resistivity of the mercury decreases from when decreasing the temperature. When decreasing the temperature, the resistivity of the mercury decreases, and suddenly at a particular temperature, the resistivity is very small and it becomes very low. We can say that the resistivity almost zero. So it shows zero resistivity. So that temperature is critical temperature. So below this critical temperature, this conductor acts as a superconductor. So here the state is superconductor. Superconducting state. So as we know that Tc the at which temperature the normal conductor transits to superconducting state is called the critical temperature. When taking the mercury, when taking example of a mercury, so when the mercury's temperature is decreasing at a particular temperature, at a particular temperature, the resistivity of the mercury decreases suddenly and fall to very low value. It becomes almost zero resistivity. It shows almost zero resistivity. So then after, it shows the property of superconductivity. So below this Tc, this conductor acts as a superconductor. So above the critical temperature, this conductor acts as a normal conductor or normal conducting state it is. So at a 4.2 degree Kelvin, it would be the critical temperature or transition temperature from normal state to superconducting state. The critical magnetic field or effect of magnetic field. Effect of magnetic field. So when a magnetic field is applied to a superconductor, then for a particular value of applied field, it loses superconductivity and becomes a normal conductor. When a magnetic field is applied to a superconductor, then for a particular value of applied field, it loses superconductivity. So this is in conductor. So it is a superconductor. When we are applying some magnetic field, so when we are applying some magnetic field to this superconductor, then at a particular magnetic field, this superconductor loses its superconductivity nature and becomes as a normal conductor. Becomes as a normal conductor. So the magnetic field for which a superconductor becomes a normal conductor is known as critical magnetic field, which is denoted by Hc and is given by the expression Hc is equals to H naught into 1 minus T by Tc whole square. So the magnetic field for which superconductor becomes a normal conductor is known as critical magnetic field. So when we are applying some magnetic field to a superconductor at a particular value of magnetic field, this superconductor changed or transits to normal conductor. So that particular magnetic field is called Hc. So at Hc, at a critical magnetic field, this superconductor transforms to a normal conductor. So here in this expression, where H naught is the field required to destroy the superconducting property at 0 degree Kelvin. H naught is the magnetic field which is required to destroy the superconductivity nature at 0 degree Kelvin. Tc is the critical temperature of the superconductor. T is the temperature of the superconductor. So when T is equals to Tc, that is when the temperature is equals to critical temperature. Then critical magnetic field is equal to 0. So when temperature is equal to critical temperature, then the critical magnetic field becomes 0. When temperature is equals to 0 degree Kelvin, then the critical magnetic field is equal to the H naught. H naught, which is a field required to destroy the superconducting property. So the variation of critical magnetic field with respect to temperature can be seen in this diagram. So variation of critical magnetic field with temperature. So taking temperature on x-axis, which is in degree Kelvin, and taking the magnetic field on y-axis. So here, when T is equals to Tc, H0 becomes, Hc becomes 0. So here, Hc is equals to H0. Hc is equals to H0. So what happens? Hc is equals to H0. So the temperature at 0. The temperature at 0, Hc is equals to H0. So where the Hc is equals to 0, where the temperature is equals to critical temperature. T is equals to Tc here. So where T is equals to Tc, so the critical temperature is equals to, sorry, the HC critical temperature is equals to 0. Okay, so when we are taking the first case, T is equals to Tc, so when the temperature is equals to, this critical magnetic field becomes 0. HC becomes 0. So where T is equals to 0 degree Kelvin, what happens? HC is equals to H0. So below this Tc, it acts as a superconducting state. That is, it acts as a superconductor. So above this Tc, it acts as a normal conductor or normal conducting state. Normal state. So this is about a effect of magnetic field. Then Meissner effect. So here consider a normal conductor which is at a room temperature. When a magnetic field H is applied to the normal conductor, then it allows the magnetic lines to pass through it. Suppose we are considering a normal conductor, and it is at room temperature. It is at room temperature. When magnetic field is applied to this normal conductor, then it allows magnetic lines of force to pass, so that it allows magnetic lines, forces. Okay, so normal conductor at room temperature, when magnetic field is applied, then it allows magnetic lines to pass through it. So thus we have magnetic field induction. So that is B. There is some B in a normal conductor. When the entire system is cooled, so now this is at the room temperature. It is at the room temperature. Now it is cooled. That is, T is less than Tc. So it is cooled. Then the normal conductor becomes a superconductor. Then the normal conductor becomes superconductor, and it will not allow the magnetic lines to pass through it. So at this temperature, what happens? So this is the normal conductor. So this normal conductor, we are taking normal conductor. Which is at room temperature. When magnetic field is applied, it allows the magnetic lines to pass through it. But when this normal conductor temperature is decreased to below critical temperature, so when it is cooled below the room temperature, particularly want to say T is less than Tc, this normal conductor becomes superconductor. Becomes superconductor. So when we apply magnetic field, H, so it will not allow. So the magnetic lines of forces does not pass through this conductor. So as it transformed into superconducting state, so that when applying magnetic field H, this superconductor does not allow the magnetic lines to pass through it. So it expels the magnetic lines. So it ejects the magnetic lines to pass through it. So this effect observed by Meissner. So it is known as Meissner effect. Thus, superconductor does not allow magnetic lines through it or expels the magnetic lines. So that the superconductor expels the magnetic lines. It will not allow magnetic lines to pass through it. So for a normal conductor, magnetic field induction B is equal to mu naught H plus M. Mu naught of H plus M. So where mu naught is the permeability of free space or permeability of the air. H is the magnetic field, applied magnetic field. H is magnetization of the normal conductor. Magnetization of the normal conductor. So for a superconductor, B is equals to 0. B is equals to 0. So that when B is equals to 0, from this expression, so mu naught, so as we know, for a normal conductor, B is equals to mu naught of H plus M. So for a superconductor, it will not allow the magnetic lines to pass through it. So that magnetic field induction B is equal to 0. So that B becomes 0 is equals to mu naught of H plus M. So here H plus M is equals to 0 and minus M is equals to H. So magnetic field is opposite to the magnetization. So applied magnetic field induces magnetization in the opposite direction. Applied magnetic field induces magnetization in the opposite direction. So magnetic susceptibility chi is equals to M by H, so that it is equals to minus 1. Minus 1. So chi is equals to minus 1. So from the above results clearly indicate that a superconductor behaves as a perfect diamagnetic material in the presence of a magnetic field. In the presence of a magnetic field. So Meissner effects prove this fact. Meissner effect prove this fact. So from this diagram, here from figure A, this is a normal conductor. So normal conductor temperature is above the critical temperature. So critical temperature means when the normal conductor transformed into a superconductor. At which temperature the normal conductor transformed into superconductor is called critical temperature. So this normal conductor's temperature is greater than the critical temperature. So when we keep this normal conductor in a magnetic field, at the temperature T is greater than Tc. It allows the magnetic lines to pass through it. So that these are the magnetic field induction. So the magnetic lines of those So it allows the magnetic lines to pass through it, so that there is a magnetic field induction B. Magnetic field induction B. So this is it. This is the normal conductor which we kept in the external magnetic field H. At temperature T is greater than critical temperature. When it is cooled below critical temperature, so that it becomes T is less than Tc. T is less than Tc. Applying some magnetic field. So that this conductor does not allows the magnetic lines to pass through it, so that it expels the magnetic lines to pass through it, so that no magnetic line is passing through the conductor. So that because of expelling the magnetic lines to pass through it, so some B becomes 0 here. B becomes 0 here. No magnetic field induction here in this conductor. So because it acts as a superconductor. So this when it is cooled to a below critical temperature, so it becomes superconducting state, so that a superconductor does not allow the magnetic lines to pass through it. So B is equals to 0, HT is less than TC. When the field is removed, when the magnetic field is removed, H becomes 0. When the magnetic field is 0, then the superconductor, so the superconducting state will be like that. So HT is less than TC. Now effect of current. So the critical magnetic field required to destroy superconductivity need not necessarily be applied externally. So an electric current flowing through the superconducting material itself gives rise to necessary magnetic field. So the critical magnetic field required to destroy superconductivity need not be necessary to apply externally. But an electric current flowing through the semi-superconducting material itself may give rise to necessary magnetic field. So for example, when a current flows through a superconducting ring, it gives rise to its own magnetic field. When a current flows through a superconducting material, it gives rise to its own magnetic field. So as a current increases to a value of critical value, that is critical current IC, the associated magnetic field becomes HC and the superconducting disappears. The induced current in a superconductor induces a magnetic field in it. If the magnetic field is equal to the critical magnetic field, H is equals to HC, then it converts into normal conductor. The current in H is known as critical current IC. If suppose R is the radius of the superconductor, then IC, critical current, is equals to 2 pi R HC. 2 pi R HC. So this limits the maximum possible current that flows through the superconductor. Hence, this is the main hurdle in the producing high field superconducting magnets. The current density at which it occurs is known as critical current density and is known as JC is equals to critical current IC by A. So where JC is the critical current density, IC is the critical current, A is the area of cross section of the superconductor. Area of the cross section of the superconductor. Now we'll see the references. Engineering Physics by K. Tyagarajan, Tata McGraw Education Private Limited. A textbook of Engineering Physics by M.N. Avadhanulu, P.G. Ksheerasagar. Publication by S. Chand and Company, Delhi. Engineering Physics by Dr. M.R. Mughal, Anuradha Publications, Chennai. Engineering Physics by P.K. Palanisamy, 4th edition, Sci-Tech Publications, Private Limited, Chennai. So these are the references which can be used to refer about this topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.